trigonometry, bearings, and coordinates. So that's just an overview of it. You will need a calculator, preferably like a scientific or graphics calculator for this lesson, just because we're going to be using some trigonometric functions on it. So I don't know if you guys can see, but this kind of calculator would be good. Or a calculator like this, as long as it has the sin, cos, tan buttons on it. All right, so let's get going. Cool. Okay, trigonometry. So you guys have probably heard of this word before, but what exactly does it mean? So it's kind of the study of triangles, and basically there's sides and angles, and we can figure out the side length of a triangle if we're given some specific information about it. So here we have a right-angled triangle. Now from Pythagoras, you might remember that the longest side, which is opposite the right angle, is called the hypotenuse. And then you've got two other sides. Now in Pythagoras, we didn't really name the two other sides. They were kind of just the two other sides, but here we actually do name them differently. So because trigonometry considers side lengths and angles, we're going to have an angle involved. And the side that is opposite the angle that it's kind of opening up to is called the opposite side. Surprise, surprise. And then the one next to it is called adjacent. So the angle is kind of like enclosed between two sides. So one of them is the hypotenuse and the other side would be the adjacent. And then the opposite side is just the one that it's kind of facing. Yeah. And here we have these things called trigonometric ratios. Now, this thing comes from similar triangles in that if you have two triangles and they've got the same angles, then we know that the ratio of their sides are going to be equal, right? That's what we went over last week. So here we have some special ratios that apply to right angle triangles. So if you're given any angle in a right angle triangle, you can use these things called trigonometric ratios to find the ratio between two of the other sides. So for example, I'm just gonna write on the board. So, for example, this triangle right here, it might have, so we'll be looking at this angle. And then we have these things called sine, cosine, and tangent. All right, so sine of theta basically just means the ratio between the side opposite of theta and the hypotenuse. So for example, we might have this triangle has lengths 4, what should this be? 3, did I just say 4 when I wrote 5? Sorry, 5, 3, and 4. Okay, so the sine of this angle would be the opposite side over the hypotenuse, so the ratio between them. So the side opposite is 3. The hypotenuse is 5. Now cosine, as we can see over here, is a over h. Now a is adjacent, so what's the adjacent side? It is 4 over the hypotenuse, which is 5. Now you might be wondering where we can use these ratios, because right now it kind of seems pretty straightforward and we don't really know why we need these ratios, but they're quite useful when we're given a side length and an angle, and then we need to find another side length, or if we're given two side lengths, and then we can find the angle inside the triangle. Okay, anyways, so tan of this angle, opposite over adjacent, we've got 3/4. And here's just a nice little mnemonic. So we've got this so katoa thing I've got here. So it's kind of just like sine is opposite of a hypotenuse. So it's like so and then katoa. And yeah, I think in middle school, our teacher always like use these little mnemonics to help us remember things. And I find that they really help. So I kind of found one that might help you guys. All right. Okay. Sorry, laptop's being a bit slow. All right. Here we've got a little bit more on trigonometric ratios. So, you can, given the size of an angle, you can actually use your calculator to work out the ratio of two other sides. So, for example, we can have, so I've got here sine 45 equals 0.71. Now, if you get your calculators out and you just key in sine 45, then you should get 0.71. Now, if you don't, it might be because you're using your calculator in radians mode or some other mode. So degrees are like a measure of angles, and radians are also another type of unit for measuring angles. So if you're in radians, your answers are gonna all come out wrong. So just go maybe into your setup and then change your degree, your angle thing into degrees. All right, so yeah, sine 45 equals 0.71. Now, once you've got that on your calculator, this doesn't really say much on its own, so we'll draw a triangle to help us visualize what's going on. So if we have a 45-degree angle here, then the sine ratio is telling us that the opposite side, so this is the opposite side, this is the hypotenuse. So the opposite side is going to be 0.71 times the length of the hypotenuse. So for example, if the length of the hypotenuse is 1 centimeter, then the opposite side is going to be 0.71 times that, which is 0.71 centimeters. So that's basically what the ratio means. And if the hypotenuse is some other length, like 2 centimeters, then this one will be like 1.42 centimeters. So this is just a ratio. It's not like some defined set of side lengths. It's just comparing the two side lengths. Right. Next slide. Okay, here, I'll get you guys to do some calculator practice. So just have a go typing this into your calculators and see what you get. And feel free to annotate your answers onto the whiteboard. Yeah, good job, Francis. Nice. Nice. Oh, sorry, for cos 88.1, what does it say? If you're unable to write on the screen, you could also like send your answers here in the chat too. Oh yeah, that's good, 0.03. Nice, good job everyone. All right, let's go to the next slide. Okay, so this is a bit of a long slide, but essentially what it's saying is that when you have a triangle and you want to find an unknown side length, then using the information, so this, remember these trigonometric ratios, they only work for right angle triangles. So given a right angle triangle, if you know one of the angles, so for example, this is 30 degrees, and you're given a side length, for example, this is 4 centimeters, then you can use this to find any other side of the triangle that you want. So for example, oh wait, but before we do anything, so we have the angle that we've been given and we need to label the sides of the triangle. So we've got the longest side here, that's H, the hypotenuse. This side is opposite and this side is adjacent, it's next to the angle. Okay, and for example, if I said find the opposite side, then what you would do is that you're given the adjacent side and you want to find the opposite side. So these two sides are involved, right? So that means that we need tan, tawa, right? So we can use the tan to set up an equation. So we know that the tan ratio of this angle right here, which is 30 degrees, is equal to opposite over adjacent. And the adjacent right over here is 4 centimeters, so we can go ahead and plug that in. And now we can solve the equation to find the opposite side. Sorry, my pen is frozen at the moment. Okay, so maybe I should give the O a bit of a nice little curl, or else it just looks like 0, which is a bit confusing. Okay, so the opposite side. Now we've got a 4 on the bottom, which we're like dividing by, right? This fraction line means divide. So how do we get rid of divide by 4? Well, we times both sides by 4. So if we have 0 divided by 4 times 4, then it's just back to, did I say 0? No, opposite. So opposite side is equal to, and then we times 4 to this side. So 4 tan 30. Degrees. And then this would be the length of your opposite side. And would someone like to type it out in their calculator? And maybe write in what the opposite side length is. Oh, yep, someone just sent through in the chat, 2.31 centimeters is exactly right. Oh, 309, 3 decimal places. Cool. Okay. Let's just go. So on this next slide, I've got one more example. So here you are given 62 degrees and where's my pen gone? Ah, there it is. Okay, so given 62 degrees, and we know the hypotenuse, the longest side, which is opposite the right angle, and we want to find this side then, which is adjacent to 62 degrees, the angle that we know. So if we have the adjacent and the hypotenuse sides involved, then that tells us that we need to use cosine. So because we need to use cosine, we can set up an equation like this. So I've got cosine of 62 is equal to the adjacent side, which is z over 20, and then we do our equation solving magic. Now, in the next example, which is right here, this is still the same method, except the equation solving is a little bit trickier because this time around, we have got the side that we want to find on the bottom. So we have the opposite side, which is 6, the adjacent side, which we want to find, and it's called z. Now, z is on the bottom, so we need to get it onto the top because that's the easiest way to solve the equation. So if we multiply both sides by z, so remember this line is dividing. So if we times z again, then that's going to cancel out. So times z, whoops. Okay, so we have 6 left on the side, z times tan 35. Then we can divide both sides by tan 35. And then we get our answer. Z is 8.57. So this one is the same method, except we've got a little bit more rearranging to do. And now here I've got some problems for you guys to try. I'll just write SOHCAHTOA on here. Okay, how about we start off by labeling the sides? So we know the angles. Whoops. See? Okay, so we know this angle. So can we start off by labeling which side is the hypotenuse, which side is adjacent, which side is opposite? Then we can use the right ratio to help us find the answer. Yeah, nice. That is the opposite side. Hypotenuse, opposite the right angle, right? Yeah, nice. So I just write opposite because I think you wrote that in there before, which is exactly right. So this other side over here, which we know, what must that be? Yes, it is the adjacent side. Okay, so now we've got these two sides involved. We've got we want to find the opposite side, and we know the adjacent side. So looking at our SOHCAHTOA, should we use sine, cosine, or tangent over here? Yes, perfect, so tangent. Does anyone want to write out an equation on the board? Yeah, perfect. And now we can substitute our values in, right, for this specific question. We've got an angle of 31.6. And we know that our opposite, we don't know our opposite. And in here it's called S. 13.4 on the bottom, which is adjacent. 10. So if we rearrange this, we're going to get S equals 13.4. So here we're multiplying both sides by 13.4. S equals 13.4, 10, 31.6 degrees. And what would you get if you solved that? Maybe type it into your calculator. All right, I just did it myself, and hopefully you came out with 8.24 km. I hope I'm right. Yeah. Cool. So that is our opposite side, 8.24 km. And on the equation on the right, on the question on the right, we have got which sides are involved. So we want to know the hypotenuse, and we've got the opposite side. So can someone circle which ratio we should be using? Sine, cosine, or tangent? Yes, nice, sine. All right, so I'll just clear this to get a nice clear board, and I'll set up the equation. So I won't go through and solve this because I think you guys get the hang of it. But we've got sine of the angle equals the opposite, which is 157, over the hypotenuse, which is z. Now, this is one of those questions where you've got the z, the unknown side on the bottom, so you're going to need to multiply through by z and do some more rearranging before you can solve that. So yeah. The next question is a bit of an application, and I'll leave that for you guys to do in your own time. It's pretty much like the questions that we just did, but because it's application, it does involve a bit of reading and a bit of thinking, because it says the measurements are taken 1.66 kilometers above the ground. So you work out the height of the tree by using trigonometry. Okay, sorry guys. And then you have to add 1.66 because the surveyor is also standing a certain height above the ground. But yeah, I'll leave that for you guys. Okay, the next one is finding an angle. So if you have a right-angled triangle and you're given two of its sides, then you can find any of its angles using trigonometry. Okay. So, for example, you have, I'll just use the basic 3, 4, 5 right angle triangle. And, oh wait, never mind. Sorry. I'll just say this is 4 and this is 5. So we know these two sides. And we might want to find, let's say this angle. So then we have to, we'll call it theta. So we'll set up our equation by first off labeling the sides. So this is hypotenuse, this is opposite the angle, this is adjacent. Okay, so now we know the hypotenuse and we know the adjacent, so we can use cosine. And then we set up our equation as usual. So cosine of theta is equal to the adjacent side, which is 4. Oops. 4 over 5. Now here comes the trick. So to kind of get rid of, because we want to find the angle, right? But we've got this cos over here. So to get rid of cos, we can use the inverse function. So this is called cos inverse. And you'll see it on your calculator. You might have to press the shift button and then press cos. And then in brackets, no wait, I'll just do this here. So we'll do the cosine, the cos inverse to this side, which kind of gets rid of this cos. So no more of that. And then over here, we'll do the cosine cos inverse of 4/5. Now, when you guys type that out onto your calculator, you're gonna, whoops, I should probably change to the next slide because that's what I've got on the next slide. So you can use your calculators by pressing the shift button and then, or like the inverse or second if, I'm not sure what kind of calculator you guys have got, and then press cos, and then in brackets type out 4 divided by 5. And, oops. Then, oh, sorry, I haven't checked the chat. So someone's just asking me what we did earlier in the class. I'll just quickly go through. So we've been doing trigonometry, which is like the study of triangles with their like side lengths and angles. And then what we've done so far is finding the finding a side length given an angle and another side length. Sorry, not very good at explaining, summarizing. But here, given the 2 of the angles in the triangle, we can find an angle. And I believe that this session is recorded. So if you want to like go back and watch it, you're very welcome to, the first half of the lesson. But for now, we'll just keep going with angles. So, oh, no, that's not what I need to do. Okay. So we've got this angle is equal to cosine inverse of 4/5. And if you type that out into your calculator, the answer that you come out with will be your angle. So here we've got 36. Ooh, I think someone's going to write the answer in. Was that? Oh, no. Okay, I'll do it in. 36.9 degrees to 1 decimal place. All right, and now here's a few more examples. So here we are given the, oops, I'll just annotate again. Pen's not coming up, sorry guys. Oh, finally, okay. So we are given these two sides and we want to find this angle. Now this side is the opposite side and this side is the hypotenuse. So we use sine because of so katoa, so. All right, so now we've got sine of g is equal to this ratio, and then we can use sine inverse to find the angle. Yeah. All right, I'll give you guys a minute or two to just do some practice with this. All right, just as a side note, for the question on the right, you've got the angle M, which you can figure out, but there's also the side, little m. And the way that you figure that out, you can use Pythagoras, which we learned last time, or you can also use trigonometry. Because once you've figured out the angle of big M, then you can use that angle and then figure out the little m side length. But yeah, two ways to go about that problem. All right, do you guys want to start off by labeling which side is which? So hypotenuse, adjacent, and opposite. Yep, nice work. Excuse my terrible handwriting. Cool. Okay, so we've got the adjacent and the hypotenuse involved in the first one. So which ratio should we be using? Yes. Right, so that tells us that cosine is the one to use. All right, so cosine, I'll give you guys a chance to write the equation over here. Oh, so not quite. Now what we would like is, so cosine is the ratio for a specific angle. So we would name the angle next to the cosine. So we would say cosine of the angle D. And then on the other side, just write that in, cosine of the angle D. And on the other side, we would have the ratios. I think Trinity was just writing. Do you want to continue maybe? Yeah, perfect. So we've got our adjacent over hypotenuse. And then we can substitute it in. So I'm just going to write it next to it because I'm a bit lazy. So I've got 17.6. 4. Nice job, Amina. That was fast. I'm actually yet to work it out myself. I'll just quickly type it into my calculator. Yep, that came out to be 34.7 on my one too. Nice. And I might just write some working. So we've got D is equal to, so on your calculator, this is what you would do. You would use the inverse cosine of 17.6 over 21.4. So that's what you would do on your calculator. And yeah, it become 34.7 degrees. Okay. Oops. Okay, here's a bit of fun stuff that I found. The song is, I don't know, you might find it cringe, but it might help you remember the SOHCAHTOA stuff. So if you're interested, have a listen like sometime after class. All right. And these slides are on the Google Classroom, I believe. Yeah, I just posted them, so it should be on there. Okay, now moving on to bearings. So bearings, they're essentially like compass directions. They're a specific kind of compass directions, and we have a lot of trigonometry problems that involve bearings, so they're quite useful to get to know. So bearings are this specific compass direction where you start at north and then you count how many degrees, if you like kind of go clockwise down, then you count how many degrees that direction that you're talking about is from north. So we might have, so for example, here we've got 240 degrees. So that's because we started at north and then we turned 240 degrees to get to this particular direction. So the bearing of this direction is 240 degrees. But bearings might also be something like, so this might be north and then our bearing is here. And this might be 45 degrees, but your bearing must have 3 digits. So we can't just have 45 degrees as the bearing. So as it has over here, it's 045. We just add a 0 in front. So that would be the bearing. And on the right, I've just got some like specific bearings for the compass directions. So you know how we've got 4 main directions? North. Well, obviously north is at north. You don't need like turn clockwise or anything to get to north. So that would just be 0. You don't need to do any turning. For east, you turn clockwise by a quarter of a circle, like that. So that gets you to east, and it's 90. And then we keep going south, west, and so on. And these directions in between are like at 45-degree increments because they're like halfway between the main directions, which are 90 degrees apart. So that would be 45. Okay. So now that we know what bearings are, we can use them to solve some trigonometry problems. All right, so here, what do we have? Okay, so I'll just draw this in. We've got north, which is, maybe I should use a brighter, eye-catching color. Okay, this is north. And we have a plane that is meant to be traveling north, but then it's blown off course by the wind. And now it's traveling on a bearing of 347. So that's like almost a full circle. So we go almost right the end, and we end up going in this direction over here. Now that means that if we make a right angle triangle out of it, we can do this thing over here. So using angles at a point, we know that this part here is 13 degrees. And now we can create a right angled triangle. So we know that the plane has flown for 120 kilometers, and we know that this angle is 13 degrees. And we want to find how far west of its original course it's been blown. So using our compass directions, so west is to the left on this diagram. So we want to find how far west, so this distance right over here. So now that we've got a right angle triangle, we can label the sides. So we know the hypotenuse, and we want to find the opposite side to this angle. So we can use sine. And we know the angle too. So we're going to do sine of 13. And we just plug the values in, and yeah, you guys know the deal with the equation. And yeah, that's what we come out to. So this was a more straightforward example. Sometimes we can get harder problems which involve more than one object, and then they all have like bearings relative to each other. So for example, we can have, so here, we've got participants in a planned orientation exercise head northeast. So they start off, so they start off at S, and then they head northeast, so in this direction. Oh, guys, it's helpful to remember your compass directions too. So I used to remember this, but I never eat soggy Weet-Bix. If you go clockwise, that would be your compass directions. So northeast is this way, northeast. So that's what we've got over here, and it's 750 meters. And then you head northwest, and notice that if you head northeast, then you head northwest, then this is a right angled triangle. And the reason that works is because if you look at our compass, so we've kind of got this northeast is here, northwest, oops, that's not northwest, northwest is here, and they are 90 degrees apart, right? So this thing right here is 90. So if you move the northwest line like across there, you still get 90. Okay, that was a bad attempt at explaining, but hope you guys get it. All right, so now we've got this triangle right over here. We've got 90 degrees here. So we have to find the distance to B from the start. So that's this side over here. And this side we'll call BS, because B here and S there. And this is the hypotenuse, right? And we know that this side is 550. And we know that this side is, oh, that side is 750, this side is 550. So we can use Pythagoras to figure out the third side, which is the hypotenuse. So in this case, BS squared equals the other two sides squared and added together. 550 squared plus 750 squared. And then we take the square root of both sides to get this. So this is from Pythagoras from last week. So in these problems, you often find that you can use Pythagoras and trigonometry in combination. Be really helpful. Okay, now that we've got BS is 930 degrees, 930 meters, sorry. Oops, meters. Then we can do an angle ABS. Okay, it's getting a little bit messy. Maybe I'll use a different color. Okay, now that we've got all three of these side lengths, we're going to use the angle over here. Okay, so this is our angle ABS. And our goal now is to find the bearing from B back to the start. So once we find the size of this angle, we can help figure that out. And that is because, so we were heading northwest over here, right? And north is over here. So this part is 135 degrees. Oops. 135 degrees. And the reason is, if we look at the co-interior, so oops, I'll just redraw it, getting a bit messy. So we're going northwest over here. Northwest. So north is over here. And between north and northwest, we've got an angle of 45 degrees, right? So this is north. Okay, and we can have another north over here. So those are parallel to each other, right? Because they're both going north. So that means that this angle here, these are parallel lines, must be 135 degrees. And we know that because these two angles, 45 and 135, they're co-interior to each other. They're like between parallel lines and they're facing each other. So co-interior. So we know co-interior angles add to 180. So that's how we got that this angle was 135. Okay, so now that we've found that, we can find ABS. And using trig, we can do the opposite side is this 750 meters. The adjacent side is 550. And sorry, I'm just circling everywhere. It's getting really messy, but okay, so this is what we've got. And then, yeah, we can solve this by using tan inverse of 750 over 550. And that gives us the size of angle ABS. Okay, so now I'm just gonna clear everything. Oh, that looks so much better. Okay, so now that we've got 135 and we've got 53.7, we can add them up and then that will be our bearing, because our bearing is like the angle if we rotate clockwise from north, right? So that's just the sum of these two angles. So yeah, that was a slightly more challenging question. Here you also needed the properties of parallel lines. So yeah, lots of these questions are very like combined with the different methods that we'll need. Okay, this is just a practice question for you guys. I think we won't go through that now because I also have coordinates to go through and we're running a bit low on time, but feel free to have a go at that in your own time and send me your solutions if you want me to have a look at them too. Okay, now coordinates. You guys have probably all done coordinates before, but I'll just quickly recap. So we've got an x-axis, which is the horizontal one, the y-axis, and then we can have points on these coordinates that tell us, so you can have these, oops, it's a different color. Okay. So we can have a point like this. So we've got 1, 2. So this x coordinate is 2, and then we've got y coordinate is 3. So we always write the x before the y. A lot of people get this mixed up, so important that X, the horizontal one, comes before the vertical one, which is Y. And yeah, that's her name. Okay, just gonna move on here. Okay, so this is moving on from trig, we're coming back to Pythagoras. So if we are given two coordinate points, then we can use Pythagoras to figure out the distance between them. And the way we do that is, so for example, we have A and B, and we look at the X coordinates of A and B. And that means if we see that A is at the X coordinate of 4 and B is at the X coordinate of 10, then horizontally, they're 6 apart. So that's this right over here. And now, I'll just use a different color. We can have the Y coordinates, and we've got A at 5 and B is at 10. So that means that they're 5 apart in the vertical direction. And now look what we've formed, a right angled triangle. Okay, so now we know that this side is 6, this side is 5. We can use Pythagoras to find the distance, which is this side over here. So that's the hypotenuse of the right angled triangle. So that's AB, the distance. And yeah, following Pythagoras, we know that because the distance is the hypotenuse, so distance squared equals the other two sides squared and added together. And hopefully you guys remember Pythagoras is just the A squared, B squared equals C squared, an important formula. Okay, so that's how we got this part. And then, yeah, we can just take square roots of both sides and find the distance. All right. Okay, this is a practice question for you guys to do. Just start off by labeling the points A and B on the coordinates. Yes, nice. Good job, Francis. So is that point, that's point B and point A. Cool. Okay, now do you want to draw a right angle triangle, which can help us figure out the distance between the 2 points? Nice. Yep, great job. All right, how about some of the side lengths? Do you guys want to write that in too? So on this side, this is our, oops, I'm not writing. This is our horizontal, so we consider the X coordinates of the 2 points. We've got 3 over here and -5 over here. So how far apart are they horizontally? What would this side be? Yes, great job. It is 8. Nice, and 10. Okay, so Pythagoras time, we can figure out this side. Yes, great job. Perfect. Good job, Amina. And that is the distance between the points A and B. And I hope everyone caught on to the Pythagoras that we did. Okay, here's just a bit of an application of trigonometry in real life. So remember that plane question that we did earlier? Well, this is just one of the many applications of trigonometry in real life. So, you know how when planes fly, they have to go in a specific direction, but they can be blown off course by the wind. So they need to take into account the speed and direction of the wind, and then use that to determine what speed and direction their plane should fly in to get them in the right direction so that they can actually reach their destination. Okay.